Hello everyone. First of all, Ramadan Kareem to you and your families, and I hope you're staying safe during this pandemic. Thank you for the time and for joining this webinar. Today we're going to speak about genset sizing. Okay, so after we cover the theoretical part, we're going to jump into the CAD spec sizer and have a few examples on how to size a genset. So let's start. Okay, so the first thing we should ask ourselves when we try to select a generator, what is the number of phases required? Is it a three-phase application or a single-phase application? The importance of this lies in the proper selection of our alternator. The second important question which we have to ask ourselves is what voltage is required? Why is this really important? Same story, voltage depicts the alternator needed in this generator. We'll also have to remember that with a decrease in voltage at the same power rating or at the same capacity, with a decrease in voltage, there's an increase in current, which means it affects our circuit breaker size as well. And it's also worth noting that for the same alternator capacity or the same power rating of the alternator at different voltages, the rated power varies. It varies slightly, but it does. We'll also have to consider the frequency we're operating at. Is it 50 or 60? Now, frequency is more related to the engine part of the generator, to the rotational speed of the engine, whether it should run at 1500 RPM or 1800 RPM. And definitely, with higher rotation, there's more power generated. Now, this doesn't mean that frequency doesn't affect alternators, but since all of the alternators are basically 4-pole alternators, 1500 RPM relates to 50 Hertz and 1800 RPM relates to 60 Hertz. If there were different number of poles, this wouldn't hold, okay? So the frequency or the resulting frequency would be different. Now, this is a very basic idea here related to genset ratings or applications, type of applications. Although it's very basic, I'm gonna take some time over here to make sure that these definitions are very clear for everyone. So, first of all, we'll ask ourselves, what kind of application do I have? Why am I using this genset, or how am I using it? Is it for a prime application, a standby application, or for a continuous application? Now, what's the difference between these applications? Let's look here at this slide. This is related to prime power rating. How is prime power rating defined? And you'll notice here, guys, some points I highlighted in red because they are the most important, okay? So when we talk about prime power rating, basically in general, it means that there's no mains source available, okay? My genset or my generator is my primary source of power. Now it tells me that I can use my generator for unlimited hours. So I can use it continuously. It's not that I use my genset when my primary power fails. No, I can use it continuously. It also tells me that an overload of 10% is permitted for 1 hour in every 12 hours of operation. So what does this mean? Let's look at the graph here. I'm considering a 100 kVA prime rated generator, okay? So it tells me that in every 12 hours, I can exceed this 100 kVAs up to 110 kVAs, okay? But that's only for 1 hour every 12 hours of operation. In a prime application, also, my load is variable. You see, it goes up, down. This is my load profile, guys, okay? So it's varying. It's not continuous. It's not fixed at a certain amount of power. Goes up and down throughout time. So this is a 24-hour period, and we can see how our load profile or our load varies. Now the typical peak demand is 100% of prime power rating. Okay, so that's 100% of 100 kVAs. That's 100 kVA. That's my typical peak. If I go above that, I'll be going into this overload of 10%. Okay. Now a very important point is that my average over 24 hours is 80% of the published prime power rating, which means in this case, it's 80 kVA. So this red line here is my average load over 24 hours. This should not exceed 80 kVA for a 100 kVA genset. Many people think, okay, I'll buy a 100 kVA genset. I can use it at 100 kVA continuously. No, that's wrong. Okay. Your average load factor over 24 hours should not exceed 80% of the published prime power rating. I hope this idea is very clear, guys. Anyway, if you have any questions, just note them down and we'll get back to your slide where you had a question at the end of this presentation. Now, typical prime applications would be industries, it would be remote areas in the desert where there's no mains or grid. It would be in some countries where the grid or the mains is unreliable. Okay. Now, now we'll go into standby rating, okay, but considering the same engine or the same genset, okay, which is 100 kVA prime, 110 kVA standby, okay. So this is our load profile. In a standby application, our generator is not the primary source of power. We have a mains network, okay? We have a grid which we rely on for power, and our genset is only there for emergencies. It's acting as an emergency source of power. Now, in a standby rating, no overload is permitted. No overload of what? Of the standby rating. So I cannot exceed my 110 kVAs. Okay, my standby rating, my published standby rating is 110 kVAs. I cannot exceed this rating. My load is also variable. You'll see here, if you look at this load profile, it's varying with time. Okay, it's not constant. So it's similar to our prime application. It is a variable load. The typical peak demand is 100% of the published standby rating, again, which is 110 kVAs, not 100 kVAs, my 100% of the published standby rating. Now, the average load factor over 24 hours is 80% of the published standby rating. So you see, guys, we're seeing some similarities here between standby and prime, but the rating differs. So the average load over 24 hours is 80% of the published standby rating, which is, can anyone text me or drop me a message on the chat box? If we're talking about 100 kVA prime, 110 kVA standby, what's 80% of the published standby rating? Exactly, it's 88, 90, 88, that's it. So we're not talking about 80 kVAs as in the prime application. Our average, our red line here goes up to 88 rather than this one which was at 80. Okay, so our average over 24 hours is 80% of the published standby rating. Now, a very important point related to standby application. We said here that the typical peak demand is 100% of the published standby rating, which is 110 kVA. Can we use this 110 kVA continuously? Can I use it for 3 hours, 4 hours, 5 hours, let's say? Any ideas? The answer is yes, we can. No, It's not, Abdul Karim is saying that it's 1 hour every 12 hours. That is related to prime ratings. Okay, in a standby rating, I can use my genset at 110% of the prime rating or 100% of the published standby rating for several hours, given that I do not exceed 80% as an average over 24 hours. So I can, if you look here at the graph, let's look at the graph, guys. So at hour 5, I reached 110 kVAs. I'm using it at 110 for more than 1 hour. Okay, so I'm reaching around like hour 8. So there's 3 hours of usage at 110 kVAs. That's 100% of my standby rating. There's no overload. That is 100% of my standby rating. This is fine, given that my average is not exceeding 88. Okay. Now, in standby applications, since we're pushing our engine to its limits, the maximum expected usage is 500 hours per year. Okay, 500 hours per year. Now, since we're dealing with Perkins as Jubaili brothers, Perkins state that 300 hours of those 500 can be run continuously, which is a great number, by the way. It's a very high number. Okay. Now, one might ask a question here. So if it's the same engine and it depends on usage, what would really differ in terms of prime and standby applications for the end user, for the client? If he can push his engine to work at 110 kVAs continuously, why wouldn't he? The answer is very simple, guys. Warranty. And someone here is asking about warranty. Praveen is asking about warranty. Yes. So typically speaking, for prime applications, you'll get a warranty for unlimited hours for the first year. Unlimited hours. Okay. In a standby application, you'll get this warranty for 2 years, given that you do not exceed 500 hours per year. So in case you have a genset and you experience some failure and you call us to claim your warranty, our guys can go to site, open up or connect to the controller, open up the log and check how have you been using your genset. Nadim is asking, is it only for 2 years for standby applications? Yes, Nadim. For standby applications, it's 2 years with a limit on the number of running hours. The number of running hours should not exceed 500 hours per year. No, it's not only for UAE. The warranty is not only valid for UAE. Okay? This is typical for any Perkins engine or any genset running with a Perkins engine. As for prime, we said it's for 1 year for unlimited hours. So that's the main difference for the customer's point or from a customer point of view. Okay, it's related to warranty. Okay, last but not least, let's talk about continuous power ratings. I'd like to call continuous power ratings a simplified version of prime power ratings, because that's exactly what it is. Okay, so in continuous power rating, the only difference is that my load is not variable. My load is fixed. Okay, so if my load is fixed and my average should not exceed, my average over 24 hours should not exceed 80% of my prime power rating. So what is my continuous rating? It's typically 80% of my prime power rating. It's very straightforward. So again, it's a continuous application. It's a continuous application. We're allowed to have an overload of 10% for 1 hour in every 12 hours. Our typical peak demand is 80% of the prime power rating, or in other words, guys, 100% of the base load power rating or the continuous power rating, because this is the same thing. 80% of the prime power rating is, typically speaking, 100% of our continuous or base load power rating. The average power output is 100% of the base load power rating. So ideally, if we look at the graph, this horizontal blue line and the horizontal red line should be coinciding, should be aligned, okay? But I left this gap just for you to visualize clearly, just for this to be clear. So you see here, my average is not exceeding 80% of the prime. So we're talking about the same engine, by the way, in all of these three. We are using the generator with 70% continuous. That's even better, okay? Kabil, thanks for the note. He texted me privately. But when you use it, when you consider 70% of your prime rating as your continuous rating, you're basically extending your engine's life. As simple as that, okay? So you're giving it more room. In continuous power, will there be any modifications to the engine? No, not necessarily. Guys, Alan made a note that questions to be asked after the meeting. Thank you, Alan. He's totally right, okay? I might ask a few questions. If you have any ideas, okay, just guys, please just note down your questions. We'll get back to all of your questions at the end of the presentation. Because I know you all have commitments, and I don't want to delve into these questions and waste others people's time. So let's keep them till the end. In case I ask a question and I'd like to hear from you, please, you can text your answers. So where do we select our genset or consider continuous applications? Typically speaking, in data centers, because our load is fixed, our load is not variable, it's continuous. In irrigation applications, where we have, let's say, for example, a single pump powered by a single genset. My load is fixed. It's that pump and that pump only. It's nothing else. This might be interesting for some of you guys, because I know some of our attendants do work in the irrigation field. So I hope that prime, standby, continuous ratings are clear. I hope so, because this is very basic and very important information. Now, another thing that affects our decision in selecting the generator, ambient conditions. And this is very, very important, okay? Now we'll see how ambient conditions affect the output of our gensets. I'll try to justify why do we select certain generators. In many cases, customers tend to tell us, you guys oversized gensets. Not just us, any generator vendor. Okay, but the truth is we don't oversize. We take many points into consideration, which we will see all today, by the way. And ambient conditions is one of the most important. You will see here altitude, humidity, salt, dust, and heat on the slide. Now, what I'm going to focus on is altitude and ambient temperature. Other factors do affect the genset output, but it's peanuts. The effect is minimal. It's close to zero, okay? So it's not even considered. So most importantly, when we talk about duration factors, we talk about ambient temperature first and altitude second. So my engine output decreases with altitude. Any idea why does that happen? Less oxygen, Abdul Karim. You're right, less oxygen. With altitude, air density decreases. Wally also answered with the same. With altitude, air density decreases, meaning there's less oxygen or less air going into the cylinders, into our burning chambers, okay, which will result in lower power of explosion, so a lower output power of our engine. So this is related to altitude. Now, why would my engine output decrease with increase in ambient temperature? Other guys answered as pressure variation, low pressure. You are all right, guys. It's the same idea, air density, correct. So, like air density, yes, Abdul Karim, that's true. With a higher temperature, again, back to the air density. The higher the temperature, the lower the air density. The lower the air density, the less air is going into the burning chambers, so the less power output my engine is giving me. Okay. Also, with higher temperature, ventilation is less effective. Ventilation or cooling down of my engine is less effective. Okay. It's less efficient. That's why my engine output will degrade with the increase in ambient temperature and with the increase in altitude. But what about alternators? Alternators as well degrade, okay, with the increase in ambient temperature and with the increase in altitude. They degrade with the increase in ambient temperature due to less efficient cooling. That's very straightforward. Our alternator is made up of copper windings. It gets heated up when it's loaded, so it needs proper ventilation. With the increase in ambient temperature, this ventilation or this cooling gets less efficient, and thus the output of our alternator decreases. Same idea related to altitude. With altitude, air is less dense, thus it's less efficient in cooling down our machine. That's why both the engine and the alternator would experience deration with the increase in ambient temperature and with the increase in altitude. Here's a nice example. Okay, it's a hands-on example. So let's have a look here. We're considering two scenarios or two situations. One related to Dubai ambient conditions and another related to Kenya ambient conditions. So these two dots in red are related to Dubai. Okay, so in Dubai, for example, the ambient temperature is 50 degrees Celsius. Okay, so to figure out how much my engine output derates, I'll have to look at this dark purple line on the deration chart, which is this one. Okay, so this line resembles 55 degrees Celsius. Sorry, 50 degrees Celsius. Our altitude in Dubai is 0 meters above sea level. So this x-axis is the altitude in meters above sea level. So at 0, and considering this line, which represents 50 degrees Celsius, I'll see that my engine derates by around 4%. So just as an example, if my 100 is rated 100 kVA, the actual output would be 96 kVA. It derates by 4%. Okay. Now let's take Kenya as an example. In Kenya, the ambient temperature is around 40 degrees Celsius. So we look at this turquoise line, okay, which represents 43 degrees Celsius, the closest to 40. And the altitude is at 1,000 meters above sea level. Guys, please make sure that you're all muted. So, at 1,000 meters above sea level, this would intersect at this point with the turquoise line representing 43 degrees Celsius ambient temperature. I'll notice that my engine duration is around, or is exactly 5%. Okay, meaning that the same engine, the 100 kVA engine, if placed in Kenya, it would give an output of 95 kVAs rather than 100 kVA. But we're still talking about the engine. We should also consider duration related to the alternator. Now, alternator duration is given in terms of factors rather than percentages. Okay. Now, definitely, this depends on the manufacturer. Different manufacturers have different standards. Okay. So what we're considering, guys, here is a Perkins engine and a Leroy Somer alternator. All right, because this is what typically Jubaili deals with. So up to 1,000 meters above sea level, there's no duration on the alternator itself. So there's no effect whether it's in Dubai or in Kenya. Okay. However, at 40 degrees Celsius, there's no effect on the alternator output. At 50 degrees Celsius, my duration factor is 0.946, meaning that I have a duration of 5.4%. So, and let's focus at this point, please, guys. So my engine, considering Dubai, my engine derates at 4%, and my alternator derates at 5.4%. So how much does my genset derate by? We were discussing the engines and alternators separately. Okay. So my genset derates by we'll always take the minimum of both, minimum output of both. So maximum duration out of both. So I'll consider this. I wouldn't consider my 5%. So my engine derates by 4%. My alternator derates by 5.4. So this is my genset duration. Yes, Ali, definitely you'll get a copy of these slides. Okay, so the same genset, exactly the same genset, let's say 100 kVA genset, would give me 94.6 kVAs in Dubai and would give me 95 kVAs in Kenya. Now the difference is very slight, okay? However, in some cases, you'll see a major difference. You'll see a difference up to 20, 30 kVAs, okay? So it's worth mentioning and worth noting. Guys, I'm getting lots of questions here. Multiply with the cycle. Please, let's keep the questions till the end. If you can note them down, and then we'll answer all your questions at the end. Okay. Alternator insulation class and temperature rise class. I mentioned when I was going through the outline that this is a very, very important idea. And there's a very wide misconception related to these two concepts, which is insulation class and temperature rise class. So let's have a look here. I'll just, by the way, this here is a snippet from Leroy Somer alternators. Okay, this is related to Leroy Somer, but it applies to all alternators, to all other vendors as well. Okay. Okay, guys, I've been told that it's preferable to answer questions at each slide and not at the end. So I'm gonna try to do that. Sorry, guys, I just got this instruction. I'm gonna try to do that. So let's go back here to this slide and get back to all these questions. Abdallah was asking, when used generator with equipment consume high current at beginning of work and after that will be normal consumption, same like tower crane. How to choose your generator? Abdullah, I'm getting to that in the upcoming slide. Ahmed Mansour is asking, go with an example of 1800 meters above a scaffold, 22 kVA standby, 400 voltage, not taking 22 amps, frequency goes down. Mansour, the idea related to duration, which we're discussing, applies to any country. The only thing that differs is the ambient conditions and the altitudes, but the concept holds. The concept is still the same. So you can apply this to any country. I'm not gonna go through the world map now. Ali was asking if we can get a copy of the slides. Yes, for sure. Sayed asked, we will multiply with the site engine power to the rate alternator. That will be the final site rating of the genset. That's true, Ali, because in this case, the alternator duration is higher than that of the engine. Okay. I hope I answered your questions, guys. Let's go back to alternator insulation class and temperature rise. Now, as you all know, alternators are made up of stators and rotors, which are made up of copper windings. Now, these copper windings are insulated. Okay, typically they are insulated with resin. They are impregnated with resin. So this insulation can withstand a certain temperature before it deteriorates, okay, before it fails. Now the insulation class defines how much temperature can this insulation withstand. So we have different insulation classes, H, F, and B. And by the way, this applies to motors as well, in motor application rather than in alternator applications, because it's the same idea, copper windings that are insulated, okay? So class H, being the highest insulation class available commercially, okay? This chart tells me, you see this black line, guys, that looks like a stair, like a staircase. Let me just try and do this black line here. Okay, so this line defines my insulation class. So class H tells me that my winding insulation can take up to 165 degrees Celsius if the ambient temperature is 40. Let's not think about ambient temperature right now. I don't want to confuse you guys. Simply, class H means that the alternator insulation can take up to 165 degrees Celsius. Class F tells me that my insulation can take up to 145 degrees Celsius. So which is better? Definitely class H. Now, just as a note, all our alternators, all Leroy-Somer alternators, all Michelti alternators, which Jubaili is dealing with, are or have a class H insulation, which is the highest insulation class. Okay. Now, I hope this idea of insulation class is clear. Now, what is temperature rise class? You see this green bar over here? This is temperature rise class. Okay. Now, with the temperature rise class of F, I'm looking here. Okay, temperature rise class of F. You see there's a margin between the insulation class and the temperature rise class. This margin here, this reserve, is called temperature rise class. So this ensures a longer life for my alternator. What I'm trying to say, and I'm going to say it in a much simpler words. Let's say I have 100 kVA alternator. Okay, 100 kVA alternator. If I use it at 100 kVA, if I use it at its full capacity, my temperature rise class would be H. There's no thermal reserve, okay? I'm reaching my alternator's power output limit. However, if I'm using my alternator at 90 kVAs, so I'm not pushing it to its limits, so the temperature of my winding is not reaching its limits, it's just here. My alternator winding is relatively still cold, so my winding insulation will not deteriorate. I'm giving my alternator a thermal reserve. Okay, so I have 100 kVA alternator, but I'm only using it as a 90 kVA alternator. I'm not pushing it to its limits. So when we talk about temperature rise class, it's not that you will buy or purchase an alternator of a temperature rise class F or a temperature rise class H or whatnot. It's how we use the alternator. It's similar to the definition of prime and standby. It's exactly the same engine. It depends on how we use it. So same story goes here. Same story related to temperature rise class. It depends on how we use the alternator. If I'm pushing it to its limits, if I'm reaching the maximum temperature it's designed to reach, I'm considering a temperature rise class of H. If I'm considering a temperature rise class F, it means that, in simple words, that my alternator is a bit oversized for me not to push it to its limits. Let me give you a nice analogy here. Maybe it will make things even clearer. Let's say I want to purchase a car, okay? And I would like to drive this car at 160 kilometers per hour continuously every day. If I buy a family car, a normal family car, and drive it at 160, I can do that. It's designed to reach that speed. Okay, but what would I actually be doing? I would be shortening its life. I'm pushing it to its limits if I'm doing that every day. Okay, so this is like an insulation class H with a temperature rise class H. It's pushing your alternator to its limits, to its maximum. However, if I want to drive at 160 kilometers per hour every day, what if I buy a supercar and I do that? Do I shorten its life? Not at all, because it's designed to reach much higher speeds. So 160 is nothing. So I hope this analogy makes it clear. It's the same idea here. Temperature rise class depends on how we load our alternator. Now, for Leroy Somer alternators are different classes of insulation available, or it depends on the application. Insulation classes, we're offering class H insulation, which is the highest. Okay, temperature rise classes, as I said, the Dilesh, it depends on your usage. Okay, you might come to us asking us for a 100 kVA with a temperature rise class F. What I'd say, or what I'd offer is an oversized genset or an oversized alternator. George is asking for small size generators. Why to choose H, since the current will be low, temperature is related to the current? Definitely, but it's relative. It doesn't matter. The size of the genset doesn't matter. It's relative to the windings of the stator and rotor. But hold on, I'm gonna make this even clearer. Guys, I'm gonna share a screen. I'm gonna stop this presentation and share a screen of the alternator datasheet. Just a minute. There we go. Can you guys see this datasheet? Please, just anyone text me yes, just to make sure that you can. Okay, great. All right. So this is an alternator datasheet. Okay. You'll see the insulation class is H. I'll zoom in. Yes, definitely. Okay, so my insulation class for all the alternators in this datasheet is H. This is fixed. Okay, this is related to the temperature that my insulation can withstand. Now, let's go down to the different models and see what is this temperature rise class. Typically speaking, everyone who looks at this data sheet looks here in this area. They look here, okay? He'll say, for example, okay, 415 volts, I need 250 kVA, I'll go with this alternator. But what this data sheet is telling me, for this same alternator, for example, for 46D, my output, considering a temperature rise class H, with no thermal reserve, okay, remember, pushing it to its limits, is 250 kVA. However, if I consider a temperature rise class F, meaning I don't want to push my alternator to its limits, I want to extend my alternator's life. Rather than using my alternator for 20,000 hours, just an example, it would last me like 25 or 30,000 hours. So this tells me that my output, which I should consider, is 228 kVA. You noticed, considering a class F temperature rise, my alternator output is less. Okay. Now, if let's in practice, let's talk about practical situation. If someone purchases this alternator and he's considering 228 or class F temperature rise, meaning 228 kVA, can he go more than that? Yes, of course he can. This alternator is rated 250, but then he will not be respecting the limits of temperature rise class F. It's that simple. This alternator is rated 250 kVA. If I want to consider a temperature rise class F, in order to extend my alternator's life, I should not exceed this value. Okay. Is this clear, guys? Is this idea clear? Can I go back to my slides? Okay, excellent. I hope this idea is very clear now. And guys, trust me, if you grasp this idea, plenty of people in the market would have no idea what's going on. Really, there's a very wide misconception when it comes to insulation class and temperature rise class. So I'm really happy that you got this. Now, transient responses. This is related to ISO 8528-5. Okay. So to begin with, let's say we have a running genset. Our generator is running at rated voltage, rated frequency. Okay. And suddenly we apply a load. What would happen? Our frequency would dip. Okay. We suddenly apply a load, our frequency would dip. This is similar to driving a car with cruise control. My cruise control is set at 100 kilometers per hour. Suddenly I go uphill, okay? My speed would decrease slightly, then it would recover. So same thing happens here. My frequency would dip, my governor will pump in more fuel, my engine will regain its speed, and my frequency will recover. Okay, same happens. Guys, you'll all get a copy of this webinar because I'm being asked right now. You'll all get a copy of this. There's also a video recording, so you'll get that as well. Muhammad Qadir is asking, in the data sheet of alternator, there was temperature rise class H125 and H165 for the same model. Can you please explain the difference between the two subclasses? Yes, Khalid. Okay, so the one that's 165, or actually 163, that's the standby rating of the alternator. What I was discussing is the continuous rating of the alternator in two cases. In a case that's class H temperature rise, and in another case that's class F temperature rise. However, what you saw at the end, the 163, that's the standby rating. That's typically 10% more than the continuous rating of the alternator. Okay, someone is asking, all right, that he is going to be for urgent meeting. That's fine. So back to transient responses and load acceptance. And the guy who had a question related to a crane, this is really important. So back to this idea, when we apply a certain load, okay, we experience a dip in frequency and in voltage. Now, our fuel governor will act in to recover frequency. Our AVR will act in to recover voltage. So there's a dip and there's a certain time for recovery, for our genset output to recover, okay? Now, a similar thing happens when we reject load or take some load off. So our genset is running, it's loaded, someone comes and disconnects this load or turns off certain loads. What happens is that I'll have something called an overshoot or a rise. I'll have a frequency rise and a voltage rise. Again, my governor, my AVR will act in to stabilize my output. So there's a recovery time as well. So you'll see this here on the graph. So this is my overshoot and this is my dip. Okay, so load addition and load removal, or we say load rejection. Back to this, we were saying that there are three different governing classes, G1, G2, and G3, G3 being the most stringent. And what did ISO do with these classes? They actually define the maximum allowable transient response. So the maximum allowable dip and the maximum allowable overshoot and the minimum recovery time. Okay, so when I say G3 is the most stringent, it allows for lower transient response and requires shorter recovery times than other classes. So for example, I'm going to show you, by the way, here's a summary of these performance classes, G1, G2, and G3. Okay, so this tells me that the steady state frequency band, considering a G1 class, is 2.5%. What is a steady state frequency band? It's my genset in its steady state. There's no load addition or load acceptance or load rejection. Okay, this small fluctuation of frequency should not go beyond 2.5%. You'll see it's more stringent for G2. My steady state frequency band should be limited within 1.5% and 0.5% for G3. Our maximum frequency dip, okay, maximum frequency dip, minus 15%. When does a frequency dip happens? Again, when we add load, okay, with load addition or load acceptance. It's allowed to dip by 10% in a G2 class and by minus 7% in a G3 class. The maximum frequency rise for a G1 class is 18%, so that's when we reject load, 12% for G2 and plus 10% for G3. And the frequency recovery time is 10 seconds for G1, 5 seconds for G2, 3 seconds for G3. Now, same story applies for voltage. I'm not going to go through each and every one. So this is voltage, this is frequency. Same story applies. G1 is the less stringent and G3 is the most stringent. Now, just one important note. It says maximum frequency dip, for example, or maximum frequency rise. What's this maximum? Is this when we apply 100% of our genset rating? Of course not at all, okay? This is when we apply the maximum allowable load within the limits of this class. Let me, I'm gonna stop sharing again and share with you the engine datasheet. I'm gonna share my screen on an engine datasheet and we'll see how it's mentioned there, okay? So I'm gonna share my screen again here. Okay, so this is an engine datasheet. There's a section in every Perkins engine datasheet called load acceptance. And typically this tells me, you see here, this tells me that the information shown above complies with the requirements of ISO 8528-5 stated G2 operating limits. So this is a G2 compliant engine. Now, it says here that at 50 Hertz or at 1500 RPM, if I apply 65% of my prime rating, okay, in a single step, so from 0, suddenly I apply 65% of my engine rating or my genset rating, I will experience a transient frequency deviation of 9.5%. Now, here comes the most common question in the market. Can I exceed this 65%? Can the genset take 90% of its rated load in a single step or 100% of its rated load in a single step? 100%, definitely not. It cannot take 100% in a single load, okay? And sorry, in a single step. Can it exceed this 65%? Yes, it can, but we will not remain within the limits of G2. So I can apply, let's say, I can come here and apply 70% of my genset rating in a single step. But my transient frequency deviation will increase, will go over 10%, which means I'm out of class G2. Is this clear? I have one question. Is it per step load? What do you mean, is it per step load? Okay. Nadeem, what you see on the slide, it's the tip of the iceberg related to ISO 8528. ISO 8528 is much more detailed and much more thorough. And it allows for some engines up to 5 steps. 5 steps, okay? So it's not, this is per step load, considering in some cases 5 steps as per ISO 8528, but it differs from one engine to another. I should really stress on this point. It differs from one engine to another. But ISO 8528 allows for 5 steps, okay? So when we talk about these deviations or transient responses, yes, it's as per step load. Muzammil is asking, so it means we cannot load single step 100%? Not at all. It's totally not advisable. Totally not advisable. You see, Muzammil, I'm gonna just give you an analogy. Loading a genset is actually applying a brake. It's similar to applying a brake in a car. Okay? It's an electromagnetic brake that's actually happening in the alternator. Okay? It's an opposing magnetic field. So you're braking. So imagine you're driving a car at a high speed, at its full rated speed, and you suddenly, in a single moment, you drop down to a speed of 0. 100% brake. It will damage your car, it will shatter your car. So it's very highly unadvisable to apply 100% in a single step on any genset. Okay, even though some manufacturers claim that their gensets can take up to 100%, it's totally not advisable. And it's not just me talking, I've heard it from many vendors and many different suppliers. Okay. Muzammil Ismail, because sometime during test consultant ask for one step 100%. I'm getting your point. but for standby application. Okay. Normally, in such cases, you see your engine can take up to 110%, or your genset can take up to 110%. Applying 100% is very dangerous. In such cases, we oversize the genset. Okay. So it's highly not recommended. Okay. Highly not recommended. Typically speaking, if the requirement is for the genset to accept 100% load in a single step, I'd personally go with oversizing the genset even a bit, and I'd make this 100% equivalent to 90%. Okay, although some gensets do take this 100%, but it's really rare and it's highly not advisable. Okay, guys. Okay, excellent. So let me go back to step load is calculated including the starting current, or for example, 65% of the rated load without considering the starting current. Definitely the starting current is considered. But the starting current has a bigger effect on the alternator rather than the engine. We'll go into that, Ramesh. I'm gonna give you a nice example and what to do in such cases so that you won't end up with a high genset capacity or a large generator. We'll discuss this in load shedding, okay? And it's a very nice, I have some very nice example and illustration there, okay? So typically speaking, whenever we're sizing a generator, we also have to account for future expansion. Now this slide is not very important, but minimum you should consider 10% future expansion, okay? And below here, you'll see load growth over a period of 10 years. Now, this is typical. This is not a rule. It's just a rule of thumb, okay? For different applications or like medical centers or hospitals or whatnot, you'll see different growth or load growth over a period of 10 years, which is equivalent to the numbers you see here. So I'm not gonna spend much time here. At the end of the day, this is a client preference, okay? It's up to the customer or the client to decide whether he wants to account for future expansion or not. But we as suppliers, we always recommend that you do so. Anytime, at least 10%. Always consider load growth. Ramesh is asking step load is calculated including this. Okay, we've answered that. Dilesh is asking industry load growth percentage. Yes, Dilesh, this is what you see on the slide here. I'm telling you, this is just a rule of thumb. It's not like it's up to you at the end of the day. It's up to the client and how much he'd like to consider, or if it's accounted for during the design stage. So it varies from one project to another. It varies from one country to another. Okay. So I just added this slide just to grab your attention that sometimes we do account for future expansion. What do you mean, leaving room for another genset? No, actually, it's in some cases you'd oversize the genset to account for future expansion. Just like we sometimes oversize distribution boards, we oversize breakers to account for future expansion, for future additions of load. The same applies to gensets. For example, my actual connected load today is 100 kVAs. I wouldn't go with a 100 kVA genset. I'd go, let's say, with a 135 or a 150, given that in the upcoming years, they might add some load. But again, this is, again, I say this and I stress on this. This decision is up to the client. It's a discussion between the vendor and the client, whether they want to account for future expansion or not. Said is asking, what is the OEM recommendation to put minimum load on a genset in percentage and duration of minimum load? The minimum load recommended is 30%. This is not related to our discussion. Said, if you'd like, yeah, 30 to 40%. So Said, if you'd like, we can discuss this later on. Now, genset starting time. So typically it's around 10 seconds. And this refers to the ability of non-paralleled or standalone generators to reach the rated frequency and rated voltage within 10 seconds from receiving the signal. Now I'd like to tell you where this 10 seconds came from, okay? It's not very accurate when we say that the genset should reach its rated voltage and rated frequency in 10 seconds. Okay, so typically when we're after this 10-second starting time, we'll have to introduce some starting aids. We need fully charged batteries, so we'll add a battery charger, a static battery charger. A jacket water heater would be there to keep our coolant at perfect temperature, at minimal temperature, okay? An anti-condensation heater to ensure that our windings are dry. And we need a readily available supply of clean fuel, and that's why we add fuel water separator. In some cold areas, we do also recommend oil pad heaters to make sure that the lubrication oil is at the proper density, okay, and it's not clogged in any part of the system. Okay. So where did this 10-second come from? Actually, it came from NFPA 110 type 10. And it's not really 10 seconds for the genset to reach rated frequency and voltage. So if a consultant comes around and tells you, I need the genset to be ready in 10 seconds, or I need the genset to comply with NFPA 110 type 10, you can simply answer NFPA type 10 110 is not strictly related to the genset, it's related to the entire emergency system. So you see there's NFPA 110 class, there's NFPA 110 type, and there's NFPA 110 level. Today I'm just gonna talk about NFPA 110 type. Okay? Because this is where the 10-second requirement comes from. So the type defines the maximum time in seconds that the emergency power supply system will permit the load terminals of the transfer switch to be without acceptable electrical power. So it's from the moment you lose mains power to the moment power is recovered on the ATS terminals. That is the time defined by NFPA 110. Okay, so when we say NFPA 110 type 10 is 10 seconds, this doesn't mean that my genset should be ready. What Abdisalan is asking, what is NFPA stands for, please? It's National Fire Protection Association. They set codes, they set standards. Okay, so it's like ISO or NEMA. Okay, so it's National Fire Protection Association. So back to our discussion, 10 seconds are not for the genset to reach rated voltage and rated frequency. Okay, it's for the entire emergency power supply system to recover. And why am I emphasizing on this? Because many ask for a type NFPA 110 type 10 compliant genset. But guys, it's not just related to the genset. There's the ATS as well. Okay, and we'll see here. This is what happens when we suddenly lose mains power. Okay, so there's a sequence of events. So the ATS detects mains failure. There's a programmable delay in the ATS. Then the ATS sends a start signal to the DG control panel. So this takes around 1 second. Okay, so this takes around 1 second. Then the diesel generator controller initiates the start sequence. The engine runs and starts. It reaches rated frequency and voltage. that should typically take around 8.5 seconds. So you'll see here, guys, the genset should actually take less than 10 seconds to reach rated voltage and rated frequency to be compliant with NFPA 110 type 10 to account for other time related to ATS transitions. So after it reaches rated frequency and voltage, the ATS transition to neutral position, there's a programmable delay there as well, and the ATS transition to, this is not neutral, guys, sorry, this is a typo, ATS transition to emergency position. Okay, so the entire process here should take 10 seconds maximum. .5 seconds for the genset to reach steady state, including cranking time of the engine. Yes. Yes, including cranking time of the engine. It's very stringent, by the way. Huh? It's very tough to comply with. What is the service factor? What service factor? What do you mean, Said? I didn't get your question. Service factor related to what exactly? Guys, if your questions are not directly related to the content on the slides, please postpone them. We'll tackle them or discuss them later on. So, load demand factor. Should we consider, yes, please drop me an email. Should we consider total demand load or total connected load when it comes to sizing a generator? Now, typically speaking, and out of my experience here in Dubai, DEWA enforces relying on the total connected load when it comes to emergency power supply systems. There might be other regulations in different countries, but to be honest with you guys, I'm not aware of. Okay, but I know for a fact that DEWA requires all diesel generators or all emergency power systems to be sized as per total connected load. And actually, this gives us a margin of, let's say, of ease, of relaxation. Why? Because you know that at some point, in some cases, you're oversizing your genset and you won't face any issues because the actual load is the demand load. Okay, it's the total connected load multiplied by a certain demand factor. And in some cases, demand factors are really high. For example, if you look here, this is an example of different loads. If you look at arc welders, for example, the demand load, the total connected load is 30 to 60%. So this is the demand factor of the total connected load. So 30 to 60% of the total connected load. Typically speaking, in residential buildings, it's 80%. Okay, so the demand load is around 80% of the total connected load. So let's say you have a total connected load of 100 kVA. Your total demand load is actually 80 kVAs. DEWA is forcing you to size your genset as per your 100 kVAs, which means you're in a safe zone. You have nothing to worry about. So this is the formula. It's the total operating kilowatts over the total connected kilowatts divided by 100. It gives you the demand factor. Normally, it's the other way around. You have your total connected load, you have your demand factor, then you can get your total demand load. Now, load types. Okay, so this is just to tell you that there are different load types that would affect sizing of the genset, especially nonlinear loads. Nonlinear loads, I'm not gonna really focus on this. This is a different subject, but it's just to grab your attention that this does affect the genset size. Okay, so nonlinear loads, guys, are loads that change their impedance with the change of voltage. Okay, so current is not actually proportional to the voltage. Okay, which will induce different harmonics and it will affect other loads and the power source as well. Okay, so an example of these fluorescent harmonic loads or nonlinear loads are fluorescent lamps, gas discharges, UPS, computer equipment, Okay, harmonic free loads or linear loads are basically resistive loads. Current is proportional to the voltage, so you will have no effect on the power source or the load itself. In a nutshell, guys, when we have harmonic loads, we tend to increase the genset size to account or to mitigate the effect of harmonics. As simple as that. We shouldn't really get into more details related to this, because typically you won't do manual sizing when it comes to harmonic loads. This is a more interesting subject, and is closer to all of us, let's say, closer to reality. It's motor starters, okay? You know, we have different kinds of motor starters. You know that connecting a motor directly to the power source would yield or result an extremely high starting current, in some cases up to 7 and 8 times of the running current. For example, I'm just throwing in numbers as examples, guys, okay? So if you have a motor that's rated 5 amps running, so that draws 5 amps while it's normally running, if I connect it directly to the power source, which we call DOL or direct online connection, it could draw up to 35 amps when I initially start this motor. Okay. Now to mitigate the effect of starting current, we add what is called a starter. So a Y delta starter, or a star delta as it's called, is the most common starter, and it decreases the starting current up to around like 2.5 to 3 times the running current. So again, the same motor which draws 5 amps while it's running, equipped with a star delta or a Y delta starter, will have a starting current of 2.5 to maximum 3 amps. Okay, so this graph shows you basically the difference between DOL. This is DOL. Okay, my starting current is 6 here. If I'm using a star delta or a Y delta starter to run the same motor, my starting current would drop down to 2. Okay, so you see there's a big difference there. Now, which is more convenient for me if I'm sizing a genset to feed this pump? Definitely considering a Y delta starter. Definitely not direct online, because my genset, although this is not the running load, my genset should have the capability or the capacity to feed this load and to provide this starting current. Okay. There's also a soft starter. Kindly give an example how to correctly size the genset for starting motor current, because after running motor, the amperes goes very low. That time our genset is running under load. I need more details on it. Okay, Muzammil, I will give you more details on this. Okay, but I'm gonna go through the different starter types. I'm gonna wrap up this discussion, and we'll talk about real examples and like actual engine alternator selection from the Perkins and Leroy Somer or Michelti leaflets. But I cannot do this right now. Okay, we'll do this later on. So please contact me after this training session. Okay, guys, please bear with me. I'm almost done. Some people are asking how much time is left. I'm almost done. Please bear with me. What's coming is really important. Okay, and thank you all for your patience. So soft starters are programmable starters. You can actually program the incoming current, okay, or the starting current. So it could be like 200%, 300%, and whatnot. The best of all, but the most expensive, it's really costly, is the VFD or the VSD, which is a variable frequency drive or a variable speed drive. And using this kind of starter, I can consider that my starting current is equal to my running current, okay? My factor is 1. There's no addition at all. So typically, this is the best scenario for someone who is sizing a genset. Okay, it's the most straightforward, but it's really costly. Now, this is, guys, this is the last topic we're going to discuss. I'm going to leave some room for questions and answers related to this, okay? Since we've answered other questions too as we were going. So load shedding, lots of words here, okay? Load shedding is the operation of temporarily reducing the supply of electricity to an area to avoid overloading the generators. A generator cannot take 100% of its load in one go, typically speaking. This would cause the frequency and voltage to drop too much. This generally means you have to oversize the generator so that it can comfortably accommodate the initial site load. Okay, this at times can be expensive. It is possible, however, to avoid this cost by implementing load shedding. This involves putting a delay on some of the circuits within the building. The initial load on the generator is therefore within the acceptable limits. Too much words. In a nutshell, guys, load shedding is step loading. Okay, it's when I have a certain load and I divide this load into various steps rather than applying it all at the same time. Following here, I have a very nice example. Okay, so let's consider that our load is comprised of 3 pumps, 3 identical pumps. Okay, and for the sake of brevity and ease of explanation, let's say that the current rating of this pump, of one pump, is 10 amps. So this is when my pump is running. Okay, it is equipped with a Y delta starter, and my starting current is 25 amps. Now, I'm gonna consider 2 scenarios, one where we apply all the load at once, and another where we apply load shedding or step loading. So let's say I get all of these 3 pumps and I start them at once. What would happen? If my starting current is 25 amps and I've got 3 pumps, I will have an overshoot up to 75 amps, correct? Because it's 3 times 25. I've got 3 pumps starting at once. Then my pumps will be running. There will be a drop in the current intake until I reach a stable 30 amps. Okay, so this 30 amps is 3 pumps running. It's 3 pumps running, each drawing 10 amps. Guys, can you please mute your mics? I'm almost done. Okay, so I ended up with 30 amps. Guys, someone has his mic on. Can you please mute? Okay, so I ended up with 3 running pumps, each drawing 10 amps. That's a total of 30 amps. Versus a case, excuse me, just a minute, guys. I'm gonna mute everyone.
No, that is why we have put the question also. You can see that. Yeah.
Okay, sorry guys, back to the presentation. Versus a case where I apply load shedding. So let's say I start with the first pump. I started, okay, it will reach a maximum of 25 amps and then it will drop down to 10. I wait for a few seconds, okay, I wait for some time. Then I apply my second pipe or I start my second pump or my second step, okay. So it overshoots up to how much? Overshoots up to 10 plus 25. That's 35 amps, okay. That's 35 amps. And then it drops down to 20. Now here at this point, I have 2 pumps running. I'll wait for some time, okay, and then I will apply my third and last pump, my third step. It will overshoot up to 45 amps because it's 20 plus 25, that's 45, and then it will drop down to 30 amps. That's 3 pumps running at this point. Okay, so what's the biggest or the main difference here? Look, guys, in case number 1, I overshoot it to up to 75 amps versus applying load shedding where we only reached 45 amps. That's a major difference. It's really big when it comes to sizing the generator to feed these 3 pumps. So the same load, the same pumps, much bigger difference in current. So this, applying this load shedding, this scenario here, okay, I would pay a little extra to apply these timers between loads, and I would greatly save on my capex and my opex because I'll end up with a smaller genset, that smaller initial cost, less fuel consumption in the future, less maintenance costs. So you'll see the effect of load shedding is really, really huge, okay? And it's really important to consider it in such applications. Any questions related to this slide? Okay, guys, so just to wrap up, we've talked about number of phases, voltages, frequency. That's the most basic questions to ask when we size a genset to be able to select the proper engine and the alternator. We've talked about different applications, and I hope this idea is really clear for you now. Prime, standby, and base load or continuous load. We've talked about duration factors, typically altitude and ambient temperature. We've discussed the idea of planning for future and future expansion. We've also had a very nice example of load stepping, okay, when we discussed load shedding, and we also discussed different motor starters and their effect on starting current. Now, considering all of these, if you have, let's say, a given load schedule with hundreds of loads, typically you'd start off by selecting an engine and alternator that would cover all this running load. In case you have harmonic loads, which we briefly discussed, you'll go to a sizing software. Now we at Jubaili, we have our in-house developed sizing software. I can recommend a few, by the way, that are open source. There's CAT Spec Sizer, which is developed by Caterpillar. By the way, Perkins is a Caterpillar owned company, so I'm not advertising for any competitors here. There's also MTU's MS size or MS spec. So these two I'd really recommend. They're very good sizing tools. Actually, Muzammil, it's not downloaded. It's an online platform. It's an online tool. Okay. If you'd like, I can go through this. Yeah, the second one actually is developed by MTU, and it's called PS Spec. Okay, PS Spec. All right. Anyway, this is just for your personal information. Okay. I'm not gonna go through this now. I'm just giving you some recommendations because these are open source and it's like free to use. So why not? They would give you a really good idea on the required generator size if you have a given load schedule. Okay. So this is it for today. Thank you all for attending, and I hope really that I answered your questions and you got what you were expecting from this presentation.